Okay, this lecture should be pretty short and sweet, so that's nice for you. What we're going to do is pick up from where we left off in class last Thursday. So I was just beginning to introduce to you uniform circular motion. We talked conceptually about what that means. And I threw 3 equations at you, which I will rewrite on the board here in a second. And what I would like to do in this lecture is just run through 3 practice problems together to look at how we can problem solve with uniform circular motion. So just as a quick refresher, uniform circular motion happens when something is rotating at a constant rate. So the speed with which something is spinning or circulating is going to stay the same. If the speed is the same and we're in uniform circular motion, we would also say that the radius of rotation is the same, and the centripetal acceleration is constant. So we talked a lot about centripetal acceleration in class on Thursday. We're going to explore that a little bit more with a lab in class on Tuesday. But the first equation that I gave you on Thursday was the equation for this centripetal acceleration. So I call it A sub C because that's what your textbook, I know you're not looking at that much, but that's what your textbook calls it. And we say that this is equal to V squared divided by R. Now I'm repeating myself, but I'm going to mention again because so many of you are going to take a college level physics at some point. This centripetal acceleration is also sometimes called radial acceleration. So centripetal and radial acceleration, they're the same thing. It's just a matter of semantics. So this is going to be directed inward, always towards the center of the circle. And the nice thing, as I mentioned last week, is since that V is squared, we don't need the direction on velocity, which is very nice because it's always changing. We're going to want our velocity in meters per second, and we're going to want our radius in meters to calculate this one. There's 2 other equations I showed you. One was the equation to find this rate of rotation. So what we do is we take the circumference, which is going to be the distance around, obviously, the distance around the rotation, and we divide it by the time it takes to go around one rotation, which we call the period. So 2 pi r divided by t will give you the, I write v, but this is really the average speed as something is rotating. Remember that velocity is always changing. Again, we're going to want our radius in meters to solve for this, and then that t, the time to go around one revolution, is going to be measured in seconds. And then the last equation is really not a new one, right? It's just a rewrite. So if we say the sum of all forces is equal to m times a, this is Newton's second law of motion, which we've been spending so much time on recently. If we write this specifically for uniform circular motion, we could say that the sum of all forces towards the center of the circle is equal to m v squared over r, because the acceleration that's happening is equal to this v squared over r. Again, this only works in uniform circular motion. So we're going to look at other types of rotation later in the week, and that third equation is not necessarily true there. Okay, so in terms of problem solving with these can be pretty easy, as maybe you're guessing. The first 2 really is a matter of plug and chug, basically. This third one, because we've got the sum of all forces, and you've seen how tricky that can sometimes get, this one can be a little bit more involved. We will certainly not be doing problems like of the caliber we were doing in the last chapter, but we will look at more in class with this one. But we'll look at what happens if there's more than one force and sort of how we diagram that and use this equation. Okay. So in the guided notes, there are 3 problems, and that's what I'm running through right now. So the first one is almost insultingly easy, but that's good, right? Let's start off with something easy. So the first problem says, a jet plane traveling 500 meters per second pulls out of a dive by moving in an arc of radius 6 kilometers. What is the plane's acceleration? And then they ask us actually in G's. I'll talk about that in a minute. But basically, what's the plane's acceleration? Okay, so the plane is traveling 500 meters per second. So this is its velocity, 500 meters per second, and it's in a dive. Certainly something that I hope none of us ever experienced in a plane, unless you go fly for the Air Force or something like that. So the plane is diving, and so it's going to pull out of the dive, as you kind of have seen, I'm sure, in videos. So it's going straight down and pulls out of the dive with an arc, right? You can't just go straight up, so it's kind of rotating, for lack of better words. And that radius of rotation is 6 kilometers. And it asks us to find the acceleration, and it actually says in G's. Okay, so let's find the acceleration. I'll explain this in G's. We might have done this already. I'll explain that towards the end of the problem. Okay, so finding the acceleration, this is going to be centripetal acceleration. It's very, very easy. So it's going to be v squared over r, truly a plug and chug. The one thing we need to be careful about here is they gave us the radius in kilometers, and we need to have some uniformity between these units. So my velocity is in meters per second. I'm going to want that radius in meters too. So 6 kilometers, there are 10 to the third or 1,000 meters in every kilometer. So 6 kilometers is equal to 6,000 meters. That's a pretty big radius. I mean, again, we're talking about an airplane. It's a big object, so that makes sense. So we say the acceleration is equal to v squared, which is 500 squared, divided by r, which is 6,000 meters. And so in units, this is meters squared per second squared divided by meters. So that's going to give us the meters per second squared. Let me put it in my calculator. So I get about 41.67 meters per second squared. Okay, so that is the acceleration of the airplane as it's coming out of the dive, 41.67 meters per second squared. Now they ask us to put this in G's. 1 G is just equal to 9.8. It's like, you know, so essentially we're finding out how many times the acceleration of gravity is this acceleration we experience in the plane. Our bodies, this is something we'll talk about a little bit more in class, but our bodies can only handle certain accelerations. Like, so acceleration is obviously tied hand in hand with force. And there's a certain amount of force like my physical body can withstand. And everybody's a little bit different, but there's, you know, a certain amount of G's where one would black out or pass out, eventually be crushed. So you've experienced some of these higher G's if you've done something like ridden a roller coaster. So you feel yourself like pushed back into the seat. And if you tried, I don't know, maybe you're so freaked out. This is me. I'd be so freaked out on the hill, I don't even try. But if you try to like lift your arm, it's going to feel heavier. If you try to move your limbs, it's going to feel heavier and hard to move. So the higher these G's get, the more dramatic that feeling, because the higher the force is. And again, there's a certain point at which your body can just handle no more. And in flight, that's important, because if you're in you know, some kind of a military plane, like an F-16 or something, and you're experiencing an acceleration that causes you to black out, and you're the pilot, that's clearly very, very dangerous, right? So, for instance, when pilots were trying to break the sound barrier in the 1950s, 40s and 50s, many died because they would black out because of these crazy accelerations, and then crash the plane. So anyways, that's where that's coming from. So for all intents and purposes, we'll take our acceleration, 41.67 meters per second squared, and this is just a conversion. That's all this is. So we say 1G is equal to 9.8, so I'm dividing by 9.8 in this conversion. So I'm taking 41.67, I'm dividing it by 9.8, and I get about 4.25 G's, which people can handle that. It's when we're getting into the area of like 10 plus G's that people start to, you know, black out and things like that. So 4.25 G's is what this pilot experiences. Again, I went off on a tangent on G's. On my lecture, I promised would be short. But to solve for this acceleration is very simple, completely plug and chug. The only thing that we really had to watch here was our units. So we had to convert those kilometers into meters. Okay, so let's look at sample problem number 2. Let me grab the eraser, which is a little bit harder. Okay, sample problem number 2 says, calculate the centripetal acceleration of the Earth in its orbit around the Sun and the net force exerted on the Earth. What exerts this force on the Earth? Assume the Earth's orbit has a radius of 1.5 times 10 to the 11 meters. The other thing we're assuming here, I don't know if anybody knows watching this video, the Earth, so planets don't orbit in a perfectly circular orbit. We're going to assume this is, okay? So this is the Sun. Here's Earth, and it is rotating around the sun. And so the question asked me to find that centripetal acceleration and to find the net force. And they tell me that the radius of the Earth's orbit is equal to 1.5 times 10 to the 11 meters. There's one other thing I should have typed up in this problem. I have weird numbers in my head and I forget to put them on the PowerPoint. The mass of the Earth is something I'm assuming you probably don't have memorized, because why would you? But the mass of the Earth is 5.98 times 10 to the 24 kilograms approximately. We'll talk in the next chapter about how they came up with that. But you need those two numbers, so pretend that was given as well. Okay, so we want to find the centripetal acceleration of the Earth. So, okay, centripetal acceleration is equal to v squared divided by r. We know r is that 1.5 times 10 to the 11 meters. I have no idea what v squared is, or v. So then I'm thinking, okay, I got to find v. And I have the second equation for v. V is 2 pi r over t. So let's go to that. V is equal to 2 pi r over t. Okay, so I know the whole top, 2 pi r, I know that. The question is, what is t? Do I know the period, the time it takes for one complete revolution to occur? And yes, I do. So this is supposed to be kind of common knowledge, they would assume. The period of this rotation is what we call 1 year, right? It takes 365, approximately, it takes 365.25, because of leap day, days for this rotation to occur. So we will want that in seconds. That's going to be a little annoying. But if we look at what we've got here, that allows me to find v, right? And then I can plug that in here, and I know my r, and now I've got a. Okay? Now, normally, I would prefer to take this in variable form and put it in. So where I have v, write 2 pi r over t, square it, simplify, plug and chug. But I think it's kind of interesting to see how fast the Earth is moving in its orbit around the sun. So I'm going to actually plug it in numerical form here, just to get the velocity of the Earth around the sun, and then plug that in for the acceleration. Okay, so let's convert a year into seconds. That's going to be a good time. So 1 year, let's call it 365.25 days to be proper. If you were solving this problem on a quiz and you said 365, that's fine. Okay, so there's 365.25 days in a year. And I'm going to get this into seconds. So there's 24 hours per day. And let me convert hours into seconds. So there's 3,600 seconds per hour. So these units convert out. You give me seconds. I'm going to put it in scientific notation, which means I'm definitely rounding. So this is approximately, no, let's write the whole number out. 315,57600 seconds. All right, so what is that? 31,557,600 seconds in a year. And so we can find the velocity of the Earth. So the velocity is equal to 2 pi times r, which is 1.5 times 10 to the 11 meters, divided by the period, which is that 315,57600 seconds. Now I'm doing a lot of things that we always tell you not to do, like in all of your other science classes, this is a no-go. You should put this in scientific notation and shorten it, but I just want to get a pretty precise number. The other thing I'm going to do is for pi, I'm not going to leave that as pi, which you would do in a math class. I want to know, like, how fast is this thing actually moving? So I'm going to put in my 3.14 to get a number. Okay, so when I calculate that out, I get, sorry, awkward pause while I put it in. Um, 29,850, let's just leave it there, meters per second. That's pretty impressive. So the Earth in its rotation around the sun is going close to 30 kilometers per second. That's really fast. So we're all moving at that speed with it. And just to be clear, I'm looking at one type of motion for the Earth, right? So this is the Earth in its large orbit around the sun. I'm not calculating for the spin on its axis, which makes our days, nor are we looking at the motion of our entire solar system with respect to the galaxy, or galaxy in the universe. So the point is we're moving, man. We're moving all the time. We just don't have a sense of it because we've evolved to be used to that. So anyways, this is the velocity of the Earth. So if I'm going to find this acceleration, the centripetal acceleration of the Earth is 29,850 meters per second squared divided by r, which is 1.5 times 10 to the 11 meters. And so when I put this in, we're actually going to get a pretty small acceleration. I get about 0.006 meters per second squared. That's really small, all right? So even though we're moving at a really big clip, the acceleration on Earth is quite small. What is causing that acceleration? This is something we'll talk about a lot more in the coming weeks. I'm going to guess you would all guess the sun, and that is correct. It's actually the mass of the sun that's causing that acceleration. Yeah, a couple weeks from now we'll learn about space-time. It's actually kind of a dip in the fabric of space causing that acceleration, so it's pretty cool. Okay, so pretty small acceleration. And if we were going to go for the last part, find the net force causing that acceleration, we'd say the net force is equal to mass times acceleration, or v squared over r. And so the mass, we put in the mass of the Earth, 5.98 times 10 to the 24, and the acceleration, we put in this 0.006. So we're going to end up with a really large force because this is a big, big mass. But again, that large force does not cause a huge acceleration because the Earth is such a large quantity. Okay, so that was a little bit longer. Again, it wasn't really, hopefully, hard. There were just a lot of numbers to deal with. So first having to find that velocity so that we could go handle the acceleration and then plug that in for a force. So again, I wasn't really doing algebra or anything, but numerically that was a little bit more to handle. Okay, let's do the final problem. It's actually shorter than this one. All right, the final problem. A horizontal force of 280 newtons is exerted on a 2-kilogram discus as it is rotated uniformly in a horizontal circle of radius 1 meter. Calculate the speed of the discus. Okay, that was like a mouthful. Let me write down what I wrote, and then I'll kind of help you visualize, I hope. Okay, 280 newtons is the horizontal force. So we have a force that is 280 newtons. It's exerted on a 2-kilogram discus, so mass, 2 kilograms. As it is rotated uniformly in a horizontal circle of radius 1 meter. Calculate the speed of the discus. Okay, so to visualize this, we're going to do this in class on Tuesday. We're going to do a flying pig lab. I'm actually excited about it. We have these pigs that fly from the ceiling, and they're going to spin parallel to the floor. But maybe you remember on Thursday in class, I was spinning my lanyard all around, and I did a very poor job at it, to spin it over my head. But this rotation, as being described, is something that's rotating parallel to the floor. So imagine me spinning something up over my head, but parallel to the floor. That's what's happening. So when they say horizontal force, that's like my lanyard pulling on the keys the other day. That's that horizontal force. So this is going to be the force causing the centripetal acceleration. We know the force, we know the mass, we know the radius. We want to find the speed. Okay, so they gave me force. I'm going to think to use this equation because it's the only one with force in it. We say the net force is equal to mv squared over r. The only force that would be acting, causing centripetal acceleration, so causing this acceleration, v squared over r, would be this horizontal force. Again, hopefully we can visualize this a little bit better if you want a physical example in class on Tuesday. So for now, maybe just trust me and we'll get more into that. But we know, the point is, if we look at this equation, I know the force, I know the mass, I know the radius. I'm wanting to find the velocity or the speed. So I'm just going to do a little bit of algebra. I'm going to multiply both sides by r. And then I'm going to divide both sides by m. And then to isolate v, I'm going to take the square root of both sides. So we can say v is equal to the square root of the radius, which is 1 meter, times the force, which is 280 newtons, divided by the mass, which is 2 kilograms. So this is a square root of a little bit less than 144, so it's going to be just under 12. Let's see. Square root 140. 11.83 meters per second. And there we go. So hopefully, you've gotten to see how we can use all three of these equations in terms of uniform circular motion problems. You have a set of problems due not until Wednesday, end of the day Wednesday. But I will say to you that you can go solve all of them at this point. There's really nothing more for me to teach you. There's one other problem I want to do with you in class on Tuesday because, again, I think a physical example would be good, so I'm going to demonstrate it. So if you're solving homework problems, there's one where it has a picture. There's one where there's a picture and there's something at the top and something at the bottom, and it's asking you to find what's going on at the top and the bottom. Maybe hold off on that one if you want to work ahead, because I'm going to work on that one with you. But anything else, if you want to kind of get a head start for the week, you are ready to go with it. And I will see you in class tomorrow.